In this chapter, we will be studying quadratic functions. In this lesson, we will be studying the transformations of quadratic functions. And we will begin by looking at horizontal translations. All right, so in this lesson here, we're going to talk about the transformations of quadratic functions. Now, this idea of transformations is one that you've been exposed to earlier in your math career, and you'll come across it again in your next math course. Okay, what we're talking about here is operations that take an object, for example, and move it on a coordinate plane, that stretch it, make it bigger, make it smaller, flip it, sort of thing. And these are things that you've done before. You would have done these in like an earlier, like a junior high, where you might even put like the triangles on there and translated them and flipped them and whatnot, kind of talk about the commands like that. Now what we're going to do is we're going to do this, the exact same thing, by the way, just in a more algebraic sense. So now what we're going to do to start off with, we're going to take a look at horizontal translations here. Sorry, I'm going to adjust this a little bit so it's not quite so off kilter there. Here we go. We're going to take a look at something called a horizontal translation. And so what that means here is we're going to move things horizontally on the graph. Okay, left or right here. Now, to help you make sense of this, we're talking primarily about quadratics. So what we're going to do is we're going to start off with y equals x squared. That's the thing that we're going to translate to begin with here. Now, this is a little bit confusing, and I recognize that. This is a little bit confusing for a lot of people, how this particular concept works. So what I want to do is I'm going to try to make this as straightforward as possible. Let's say that you had y equals x squared. So I'm going to make my table of values here. Just a very, very simple table of values. In fact, I'm just going to throw one number in there. Let's say I'm going to throw 3 in here. Okay? So when I throw 3 in for x, my result is going to be 9. Okay? Now what I'm going to do is I'm going to create an expression here. I'm going to look at y equals, and instead of x squared, I'm going to change that. I'm going to make that x, let's say, minus 2 squared. Because I want to see what goes on when I change that x minus 2 in there. Now notice that it's the variable x that I'm changing very, very specifically here. So now I'm going to build my table of values. Now what I want to do here though, and this is the key to understanding this, I want to link these two together. Notice that I've changed the x variable here, not the y. I haven't done anything to the y. It's the x that I've changed. Now I know that that's the case because notice that in the original function, to get the y coordinate, I square the x. So here, to get the y coordinate, I square x minus 2. Okay, so the real function here is this squaring. So this really is taking the place of my independent variable as x minus 2. Now, if I want the dependent variable to stay the same, just think about this. If I want the result to stay the same, if I want the result to be 9, how has this affected the x coordinate? So let's just think about this. 3 squared is 9. Now what that means here is I want, in order to get 9 as a result here, I need this to be 3. Okay, I need that x minus 2 to be 3. So I need x minus 2 to be equal to 3. Now what does that mean specifically for my x value? Now watch what I got to do here. To get the x value, I have to move that minus 2 over to the other side by adding it, which means this value of 3 has to get bigger by 2. It's got to go to 5. Okay, now the whole point being here, my x value started originally at 3, and when I put x minus 2 in there to get the same result for the y coordinate, my x value had to get 2 larger. Now bearing in mind that x refers to your horizontal position, when I talk about something getting 2 larger, that means I've actually moved 2 to the right. So when I see this x minus 2 in the equation here, okay, with the square applied to it, and it's really important that the square is applied to that whole thing, okay? So x minus 2 squared meant a horizontal translation 2 to the right. Now I can get a similar sort of thing if I see that in there as x plus p. Let's go back to this. Let's say again we've got this x and this y here, and I put in a 3 and I get 9. Now if I change this and I look at this as the function y is equal to x, let's say, plus 1 squared, again I'm going to build my table of values here and I want to get the same result. So that which means I need this to be 3. Whatever's inside the parentheses there has to be 3 so that I get 9 as a result when I square it, which means x plus 1 must equal 3. Now bring the 1 over to isolate the x to get the actual x coordinate, which means I have to subtract the 1 to get 2. So the x value is 2. Now, just think about what happened. To go from here to here, the x value got 1 unit smaller, okay? Which means this graph here, okay, when the y coordinate got 1 smaller, that means horizontally my graph moved 1 unit to the left. Okay, that's what happened to the x coordinates here. So this is how I want you to understand this. When I see that x minus p here, if I'm assuming that p is a positive value, that there's no other negatives being introduced here, because I don't want to make this overly complicated. So if I see x minus p, this has moved p units to the right. If I see x plus p, then the way I have to interpret this is that this is minus some negative p value, meaning that whatever I'm seeing here for p, it's moved that graph p units to the left. Okay, so that's how I interpret this. So take a look right here. If I've got g of x is equal to x plus 3 squared, then I know that this graph has undergone a horizontal translation. I'm just going to use ht to represent that real quick. I'm not going to write out the whole thing. But this has got a horizontal translation of 3 left. Okay, because if I was to isolate the x here, I would have to subtract. The last thing I would do to bring that 3 over would be to subtract it. Okay, that's how I isolate the x here. Likewise over here, if I've got x minus 3, and I think about that, then what would be the very last thing? If I was trying to isolate x, what would be the very last thing I would do? And the answer is I would add 3, meaning that this thing is going to undergo a horizontal translation 3 to the right. Okay? Now, that means, and this is what these two boxes up here are all about here, if you see, if you've got a horizontal translation p to the right, then the actual points are doing this. So, and I know this is a little weird, and sometimes people get hung up on this, but if you see x minus p in the equation, then what's happening to the actual coordinates of the points on the graph is they're getting larger. The x coordinates are getting larger by p, so x plus p. However, if you see x plus p in the equation, then the actual x coordinates are getting smaller by a value of p, which is a little confusing here. But once you get kind of used to what's going on there, it's not so bad. So let's go down here and take a look at this table of values. Not table of values, I'm sorry, just a table here. We're going to fill this in here. I've got y is equal to x plus 1, y is equal to x minus 2. Well, let's talk about what's going on here first. This, in terms of transformation, this is a horizontal translation 1 unit to the left. So I'm asking for the translation over here. This is a horizontal translation 1 left. This one right here, if I was to get the x by itself, I would add 2 to whatever my x coordinate was equal to. I would add 2 to it, which means this is a horizontal translation 2 to the right. Now, here's where I got to get clever. My vertex here, if I talk about just y equals x squared, my vertex, would be the point 0, 0. Don't know why I wanted to write something else there. Now, if I move 1 to the left of this, that means I'm going to take that x coordinate and just subtract 1. That would be negative 1, 0. But at the same time, if I was to go 2 to the right, I would take that x coordinate and add 2 to it. So that would become the point 2, 0. In both of these cases, I have no reason to believe these parabolas don't do anything other than open up. So each one of these things is going to have a minimum value of 0. That's the y coordinate. The range, for the same reason, I'm going to say y is greater than or equal to 0, y is greater than or equal to 0. But the axis of symmetry is going to change because the axis of symmetry is going to be linked to the x coordinates here. So x equals negative 1 or x plus 1 is 0. X is equal to 2 or x minus 2 is equal to 0. And actually notice that one of the equations that I build for the axis of symmetry is simply taking whatever's being squared and setting it equal to 0. Okay? I hope that makes sense. That's one of the more, well, it's one of the least intuitively obvious things that you were going to run into in this particular chapter here, is just recognizing if I see an x plus 1, okay, and it's being squared, that it actually means 1 to the left as opposed to 1 to the right. And now we will consider vertical translations. All right, now let's talk about vertical translations. So in this case, we're going to move something, we're going to move the parabola up or down, okay, in the vertical direction here. And again, we're going to start with y equals x squared, okay, as our kind of our primary or our home function, if you want to think of it like that. Then what we're going to do is we're going to add this little q to it. Now let's just think about it like this. If I take y equals x squared, okay, and add, well, actually, let's leave it like this. Let's just start here. And in fact, let's do this. Let's go back to my table of values, okay, where I had 3 and I got 9. Let's talk about this again. So if I create a new function here, let's say y equals x squared plus 2, I want you to understand which variable here is being changed. The independent variable is being squared, okay? Now, go back to the original function right here. The y coordinate, the dependent variable, is the x coordinate squared. Okay, the x coordinate is being squared here. Now that makes this really the y coordinate increased by 2. So it really is the y coordinate that's being changed here. My x coordinate is staying the same. I haven't done anything to what's the part that's being squared. Okay, so now after I square the 3, I get 9, but the y coordinate is equal to that number plus 2. This is actually increased by 2. This goes up to 11. So what we're seeing here is that to go from here to here, when I add a 2 to that, my vertical translation here is going to be 2 up. Okay, I am adding a value to that, that y coordinate. Now, if I subtract a value, if I go right back to this, and we'll do the whole thing again here, y equals x squared, x, y, 3, 9. If I go y is equal to x squared, this time let's say minus 1. Again, x, y. Same argument here. I'm not changing the x coordinate, okay? Whatever's being squared, okay, that's staying the same. So let's say it's just 3. But when I square that, okay, 3 squared is 9, minus 1, okay, it's going to become 8. And so this thing, you can see the value of the y coordinate has changed. It's dropped. So the vertical translation here is 1 down. It has gotten 1 unit smaller. Now, this is a lot more obvious than the horizontal one, because when I see plus 2 after the square, okay, after the square, and I gotta keep saying that because I see people mess this up all the time. They try to interpret this as if it was being squared, and it's not. Since it's after the square, you just read it off exactly the way you see it. Plus 2 means up 2. Now, the reason for that here is because the y is isolated. The y is already equal to this. Now, if you think back to how we did it with the horizontal translation, I kept telling you what you need to do is you need to isolate the x and think about what you were doing to isolate the x. Well, in these cases right here, the y is already isolated. Okay? And so when we go to our image point, okay, what we would call our image point, you start with some given point on the graph and it becomes something else here. That's exactly what you would expect. 2 up, y plus 2. 1 down, y minus 1. Okay? So taking a look at a couple of examples here, if you've got y equals x squared minus 3, that's a shift down of 3 units. Okay? Or a vertical translation. You'll see me do VT quite often here. Over here, x squared plus 3. Remember, x squared is the y coordinate, and then it's being increased by 3, so that's going to be a shift up of 3 units. And again, I might just call that VT. So let's take a look at another table. Love working through tables here. Okay, so take a look at this one right here, and let's identify the transformation first before we get the rest of this. X squared plus 1, that means we have had a vertical translation of 1 up. Okay, over here, okay, well now we're starting to do a couple of things here. Now, inside the parentheses, remember that whatever's being squared, that's affecting my graph horizontally. So I have x plus 1 here. Now if I really want to understand what's going on, I got to think, what would I do to get the x by itself? Well, I would subtract 1. I would move stuff over, but eventually I would subtract 1. So that means there has been a horizontal translation of 1 left. And then I've got this negative 4 here, so that gives me my y coordinate. Okay, the x adjusted value squared. That's the y-coordinate to minus 4. So there has been a vertical translation 4 down. Over here, similar sort of thing. We're looking inside the parentheses first because this is the independent variable. That's where the independent variable should be. Okay, I've got x minus 2. Now think about it. If I wanted to figure out what was going on with the x, I would move stuff over, isolate it, and then the very last thing I would do to figure out what x is add 2. So that means we have got a horizontal translation 2 to the right. This normally, without a transformation on it, would give me my y-coordinate. My y is x minus 2 squared plus 3. So 3 up. Vertical translation 3 up. Okay, now we should be able to get the rest of this here. Because remember, we're starting off with y equals x squared. We're starting off with a vertex of 0, 0. And this one here, we've already discussed, has moved 1 up. Now that hasn't changed the x-coordinate. Nothing's happened to the x. Stayed the same. Okay, there's nothing else happening inside that square. So it's going to stay at 0. But the y-coordinate has gone up by 1. Here, to get my vertex, which should have been 0, 0, I know that this thing has been moved 1 to the left, so 0 minus 1. And it's been moved 4 down, so minus 4. Here, again, starting at 0, 0, but this thing has moved 2 to the right, so 2 to the right of 0 is going to be 2. And then 3 up. 3 up from 0 is 3. Now, max or min value, once again, and I believe we've mentioned this before, all of these are positive up front, so we know that these things open up. So they're all going to have a minimum value. And the minimum value here is going to be 1, because it's associated with the y-coordinate, which, by the way, I might as well do this right away here. That means our range is going to be y is greater than or equal to 1. Here, our minimum value is the y-coordinate negative 4, which means our range will be y is greater than or equal to negative 4. And here our y-coordinate is 3, which means our minimum is 3, and our range is going to be y is greater than or equal to 3. Which leaves us with the axis of symmetry, okay, which we've seen before is related to the x-coordinate of the vertex. So x is equal to 0, and actually when it's equal to 0, that's about the best you can do. X is equal to 0. Here, x is equal to negative 1, or if you think about the way we did it previously, x plus 1 is equal to 0. Either one of those are fine. Here, x is equal to 2, or we take what's inside that expression being squared, and I would say x minus 2 is equal to 0. Okay, and there you go. So the vertical translation is actually a little bit easier than the horizontal translation to get your head around. At least it doesn't have that rather counterintuitive step that we bump into with the horizontal translation.
In the following section, we will discuss what a vertical stretch is.
Okay, now we're going to take a look at another type of transformation. We're going to look at a vertical stretch. Okay, so this is going to be related to the a value when we write this thing out in the vertex form. Now, just really quickly here, so what we mean here is we're starting with y equals x squared, and then what we're going to do is we are going to multiply the x squared by some constant a. Now, think about this. Y is x squared. Okay, so y is x squared, and then after the squaring, because think about order of operations, I do the squaring first, then I do multiplication. So whatever x coordinate I've got, I'm squaring it to get the y coordinate, then multiplying that by a. This is a vertical transformation, okay? We're changing the vertical aspect of this. Now, I bring that up because it's not going to look vertical to most of us. Most of us are not going to see it the way we're supposed to see it, and that's okay, as long as you get your head wrapped around what's happening with the different values of a that you throw in there. And here's typically what happens. The bigger the value of a, the narrower the graph is. So you get this parabola here, and the larger the value of a, it goes like this. The smaller the value of a, the more it opens up. Now I'll explain that in just a second here. Okay? The first thing we got to just take, well, the best thing we can do here is just graph it and have a look at this. So just to see what's going on here, the dotted one here, this is your regular y equals x squared. Okay? Now, if I replace the a with 4, I want you to think about what's going on here. What I'm doing is I'm taking the y coordinate, after I've calculated, after I've squared the x, I'm taking that value and multiplying it by 4. Now, that is creating a larger y coordinate. So what's happening here is, for example, this point on the original here at 1, 1 is going to become 1, 4. Okay? The point over here that would be at 2, 4 normally is going to become 2. And then I'm going to multiply by the 4, it's going to jump up to 216. So what's happening here is the graph is getting taller. Okay, these points right here are moving up. Now that's not typically what we see. Visually, most of us interpret this as the graph getting narrower. But in reality, it's actually getting taller. So if you look up here, just to give you a sense of what's going on here, we get this point x comma y on the original graph is going to become x comma a times y. Okay, we're multiplying that old x coordinate, or sorry, the old y coordinate, I should say, the y coordinate, the old y coordinate by that value of a. Now, on the other hand, if I replace a with a fraction, 1/4, then what happens here is these points drop down. So the point, for example, 1, 1 becomes the new point 1, 1/4. The point 2, 4 on the original, instead of being 2, 4, is going to become 2, comma 1, because I'm going to divide that by 4. Okay, and so that what happens here is as the a value gets smaller, the graph widens out, yeah, but actually what's happening is it's getting shorter. Okay, so now let's take a look at another table here. So again, we got some functions here, some questions about it. So when I have a 2 in front, what that means here, I'm going to jump right to my transformation here. This is going to be a vertical stretch, or VS, I'm going to do that in a little bit here, by a factor of 2. Okay, it's vertically stretched by a factor of 2. Now over here, okay, we got a lot more going on here, but what we're interested in right now specifically is what's happening up front. Now, in order to get a lot of these transformations interpreted correctly, you almost always got to read this thing left to right. Okay, just like you would anything else here. Read it left to right. So the first thing we're going to mention here is that there's been a vertical stretch by a factor of 1/4. Vertical stretch by a factor of 1/4. Now we've already gone through these ones here. Inside the parentheses, this is affecting the graph horizontally. I'm subtracting 1 from the x. Now if I was to get x by itself, I would have to add 1. So there's been a horizontal translation, 1 to the right. Now, outside of the square is what's affecting the graph vertically. Now, I've already multiplied that by 1/4, and then I subtracted 2 from it, meaning that value got smaller by 2. So there was a vertical translation of 2 down. So those are the transformations that are occurring here that we're seeing, okay, between these two functions. Now let's take a look at what the question's asking for. When you compare this to y equals x squared, the original vertex is 0, 0. It's always important, whoops, sorry, you can't even see that. It's always important to relate that back to the original here. So 2x squared, nothing is happening horizontally. Vertically, I would multiply that y coordinate by 2, but 2 times 0 is still just 0, so that actually didn't change anything. The graphs, both of these graphs are still opening upwards, so they're both going to have a min. Oh, sorry, I probably should have done this one as well. The vertex here, notice how the stretch here did not affect the y coordinate. Okay, well, it's not going to affect the y coordinate here either. Okay, it's going to stay 0. But the translations will affect it. In this case here, we've gone 1 to the right, so 0 plus 1 is 1, and then down 2, so 0 minus 2 is -2. Okay, these both open up, so they both have minimum values related to their y coordinates, so 0 and -2, and that means that my range is going to be y is greater than or equal to 0, and then here y is greater than or equal to -2. The axis of symmetry is related to the x coordinate, so either x is equal to 0 or, well, in this case here, that is the best one, or x is equal to 1, or x minus 1 is equal to 0. And now, is this going to be wider or narrower than y equals x squared? Well, because this is a value larger than 1, it did get taller, but visually I'm going to see this as narrower. Here, because the a value isn't 1, it's smaller than 1, okay, the graph is going to get, well, shorter, but we are going to see that as wider. Okay? I hope that made sense.
The final transformation we will look at here is the vertical reflection.
So now the final transformation we're going to look at here is, we call this a reflection over the x-axis. And basically what's going on here is we're going to start with y equals x squared. And then what we're going to do is for that a value up front, we're just going to make it negative. Okay? And so the a value is going to, basically, sorry, that negative value is going to change the sign of all of the y coordinates that we got. So instead of going up, okay, instead of squaring something and all the values becoming positive, we're going to throw in an additional negative outside of that, and then all of those things are going to drop down. So this actually just causes visually a reflection over the x-axis. Okay? The points very simply become this. The y coordinate just switches from a positive value to a negative value. Now if there's an a value in there additionally, great. But really what we're looking at right now is just we're making those y coordinates negative. Now really the biggest impact that this is going to have for us is that now we're going to get maximum values. Okay, because the graph is now going to open down. We're going to have like this little hilltop right here instead of having the bottom of a valley. So now let's just take a look at some functions in a table here like we've been doing. So we're going to start off again. We're going to start off with y equals x squared. We're going to, okay, look at that. The vertex is going to be 0, 0. The very first function that we've got here, okay, we've got this negative 1/3 out front. So we're going to identify the transformations. The negative, okay, means that there has been a vertical reflection. And I'm going to write that as VR, okay, vertical reflection over the x-axis. And then there was a 1/3 out front, if you don't remember that. There's a 1/3 right there. So vertical reflection and then a vertical stretch by a factor of 1/3. You want to keep those separate. Vertical stretch by a factor of 1/3. And these are two different transformations. The next one, oh, well, the next one's got a few going on here, so let's just do this in order. The negative out front is a vertical reflection. The 4 is a vertical stretch by a factor of 4. Now, as soon as I move in inside the parentheses here, I know this is going to be horizontal because it's now the x coordinate being changed. Remember, the square, after you've squared, okay, whatever's inside there, that originally in the first parabola that we looked at, y equals x squared, squaring was what got you the y coordinate. So the squaring is still what gets you the y coordinate, and then we're changing it a little bit. So what happens before the square changes the x coordinate. And this is going to be, if I get the x by itself, I got to subtract 3. So this will be a horizontal translation 3 left. And then finally, the last thing that we do once we're trying to calculate a y coordinate here is add 5. So it's a vertical translation 5 up. All right, now we can put together the rest of this pieces here. Okay, direction of opening. Well, this has got a negative in front, so this is going to open down. This has got a negative in front, so this is going to open down. My vertex should have been 0, 0 to start off with. There's been no translations here. And when you multiply the y coordinate by negative 1/3, that actually doesn't do anything, so it's going to stay 0, 0. But here, this has gone 3 to the left, so 3 to the left of 0 is negative 3. It's gone 5 up, and 5 up from 0 is 5. Now, both of these, because they both open down, they're going to have maximum values. So the maximum value here is the y coordinate, that's going to be 0. This one's going to be 5. And because they're maximum values, my range will now be y is less than or equal to 0, y is less than or equal to 5. Now, the last one we're going to look at here, is it wider or narrower than x squared? Now that deals with the value up front here, not whether it's negative or not, that's irrelevant, just the size of this thing. Because this fraction is less than 1, okay, this is going to be wider, because the graph's getting shorter here. Here, because the a value, again ignoring the negative here, because that's larger than 1, this is going to be narrower. It's going to get taller. And now finally my axis of symmetry is related to my x coordinate of the vertex, so in this case it's simply going to be x equals 0. But here, Okay, my vertex was negative 3, 5, so x equals negative 3. Whoops. X equals negative 3, or x plus 3 is equal to 0, if you want to do it that way. All right, so now we're going to take a look at just some example questions here, but really quickly, just in general, let's just take a look at what we're seeing here. Okay, when you see it written out like this, the negative here is causing a reflection over the x-axis. The A value, separate from the negative, is going to be your vertical stretch. The P value here is going to be your horizontal translation, left or right. Now remember, this is counterintuitive, so it's always opposite that sign. And then the Q is going to represent your vertical translation. Okay? All right, now let's take a look at some questions. Okay, so we're just going to do a handful of questions here just to just try a few of these. We're going to write the coordinates of the image of the point 3, 9, and that's on the graph of y equals x squared, given the following transformations, okay? So let's just take a quick look at this. X comma y is just a point on the parabola here. Now look at the transformations we're given here. A translation 2 units to the right. Okay, 2 units to the right means I'm adding 2 to the x coordinate. And 4 units down, which means I'm taking and I'm subtracting 4 from the y coordinate. Now when I describe a transformation, I'm describing what's happening to the actual point. So this is a very easy thing to do. 2 to the right, 4 down. Now we take our point 3, 9 and plug that in. So 3 plus 2, 9 minus 4, and we're going to get the point 5, 5. Okay? Now let's take a look at the next one. A reflection over the x-axis. Well, that means whatever my y-coordinate is going to be negative, followed by a vertical translation of 2 units up. Okay, well there was no mention of x whatsoever there. But the 2 units up means I'm going to take and add 2 to that particular y-coordinate. Now the reflection happens first because it's the result of a multiplication, and then I add that 2 on later. So 3, 9 is going to become 3, negative 9 plus 2, which will be the point 3, negative 7. Okay? And now let's take a look at another one here. Again, starting with the point x, y, what's going to happen here? A vertical stretch by a factor of 3. Okay, so we're going to multiply the y-coordinate by 3, followed by a horizontal translation, 3 to the left. Okay, 3 to the left means x minus 3. And so now our point 3, 9 is going to become 3 minus 3, and then 3 times 9. Okay, so our result will be the point 0, 27. Okay, that's what we're asking you to think about here. And notice that we're not putting too many transformations all together at once in these questions when we ask them like that. You might get 1 or 2 questions where you've got like everything in there, the reflection, the stretch, both translations. But in a lot of cases, that's not what we're going to do. All right, let's take a look at another question here. Determine the corresponding point on the transformed graph given the original point here, negative 1, 1. Okay, so negative 1, 1 on the point of the graph y equals x squared, and state the transformations that have occurred. Okay. Now, actually for us, it might be easier to even state the transformations that have occurred first. Okay, because when I state those transformations, that is exactly what's happening to the point here. Now, take a look at this one. Just reading this thing across here, the first thing I come across here is within the parentheses an x plus 5. Now I'm adding 5 to x, which means to get x by itself I'd have to subtract. That's a horizontal translation, 5 left. I am now adding 1 outside after the square. Thinking about order of operations, I do this last. That's going to be 1 up. So my point x, y is going to become the point x minus 5, y plus 1. And they wanted us to use the point negative 1, 1. So negative 1 minus 5, 1 plus 1. And so we are going to get the point negative 6, 2. Oops, just off the screen there. Negative 6, 2. Let's try another one. Here now, all of a sudden we're getting some more transformations, and that's okay. Again, just read it left to right. The very first thing I see here is a vertical stretch by a factor of 2. That's what the 2 out front is. Then I've got this horizontal translation, 2 units to the right, because again, to get the x by itself, I'd have to add 2. And then after the squaring has occurred, I'm subtracting that 3. That's a vertical translation, 3 down. Okay, so putting those together, we've got this point, x comma y, this general point. So horizontally, I've gone 2 to the right, so that's going to be x plus 2. Vertical stretch by a factor of 2 means multiplying by 2 and then subtracting 3. And so then I take the point negative 1, 1. That'll be negative 1 plus 2, comma 2 times 1 minus 3. And that will be, well, negative 1 plus 2 is 1. 2 times 1 is 2 minus 3 is negative 1. And so our resulting image point, that original point, your negative 1, 1 on the original function, will become this point. Okay, let's do this next one. It's about the same level of difficulty. Going across here, I see I've got a vertical stretch by a factor of 1/2, meaning my graph's going to get wider. I've got this horizontal translation 1 to the left. Think about how I'd have to isolate the x. And then a vertical translation that happens after the square, 4 down. So I take my point, x comma y. It will become the point. 1 to the left is going to be x minus 1. Vertical stretch by a factor of 1/2 means I'm going to multiply the y coordinate by 1/2. And then 4 down means I subtract 4. So now we take that point, negative 1, 1, and we plug it in. So negative 1 minus 1, then 1/2 of 1 minus 4. So what do we got here? Negative 1 minus 1 is going to be negative 2. Now a half of 1 is going to be just a half. Minus 4 would be like negative 3.5 or negative 7 over 2. So there's where our final point ends up. Negative 2 comma negative 7 over 2. And now finally, let's take a look at this last question here. I don't have a vertical stretch because the number in front here is just going to be a 1. So there's been no vertical stretch. However, there has been a vertical reflection. And then there's been a horizontal translation. That means 3 to the right. And then this last one here means a vertical translation of 7 down. All right, so now our general point x comma y, when we plug in those transformations here, 3 to the right means x plus 3. That vertical reflection means I'm putting a negative in front of the y coordinate here, and then 7 down means I'm subtracting 7 from that. And so now we take that negative 1, 1, and we're going to plug it in. So negative 1 plus 3 is the x coordinate. Negative 1 minus 7 is the y coordinate. And what do we get here? Well, negative 1 plus 3 is positive 2. Negative 1 minus 7 is negative 8. So there's our final point.